Today we are going to perform an activity whereby we're going to find the speed of sound in air. We know approximately what that speed of sound should be. Okay, we know that it should be about 340, 345 meters per second, depending upon what the temperature is. Okay, today we're going to measure the temperature, we're going to calculate the speed of sound, and then we're going to do an experiment with air columns and resonance and standing waves to try to verify that, in fact, that is the correct speed of sound. The apparatus that you're going to use in your groups is going to look something like this. Okay? You're going to have a big tube like this that's filled with water. Inside that tube will be another tube. Okay? It looks more or less like what you see up on the board here. This is the actual thing that you're going to use here. Okay? There's a pipe that's labeled with centimeters and millimeters on it. Okay, that pipe fits inside this plastic tube, and water goes inside the pipe and the plastic tube. Above that, you're going to hit a tuning fork, and you're going to hold that tuning fork above the air column that's going to have some water in it, and you're going to see when it starts resonating, see when it starts producing a loud sound. Okay, does that make some sense right now? I'll give you some details on it here, okay? Pour some water in here. First of all, you're going to want to pour the water in while the inner tube is inside the outer tube. Okay, if you pour water in like now, when the tubes are separate from one another, when the inner tube isn't inside the outer tube, you're going to fill it close to the top, and then you're going to put this inside, and then what's going to happen? You're going to have a little trouble with Archimedes, and the water is going to start overflowing. We don't want that to happen. So make sure that when you put that in there, put the water in there, make sure the inner tube is in there already. When you put it in there, make sure the inner tube is in there, but not resting on the floor. There's a rubber stopper on the end of this plastic tube, a rubber stopper down here. It keeps the water from escaping sometimes. Sometimes it doesn't do a very good job of it, but there's a rubber stopper down there that its point is to keep the water from escaping. If we put that inner tube all the way down to the bottom and in contact with that rubber stopper as we fill it with water, then what often happens is that the water goes in the inner tube, but it doesn't leak out to the outer tube. So we want to lift it up a little bit like you see in the diagram there, pour the water into the inner tube then the water should fill up the outer tube and the inner tube in equal amounts. Does that make sense? Do it while the outer tube is on the floor. Don't hold it up in the air like this, because the water is actually a pretty heavy material. Okay, you get a liter of water, 1 small liter of water weighs 1 kilogram, 2.2 pounds. It's pretty heavy. You put the water in here, if you're holding it up in the air, oftentimes what happens is the stopper isn't strong enough to hold it, and the stopper will fall out of the bottom. Even sometimes there's masking tape on them already from a previous experiment, it'll still fall out sometimes, okay? So keep it on the floor, pour the water in, that way you shouldn't have the water causing the rubber stopper to fall out and then losing a liter or so of water on the ground. Okay, that's not what we want to do with this. We get it filled with water, more or less at least filled with water. It looks something like this. We hit a tuning fork. We hold that tuning fork just like this. We hold that tuning fork above the white plastic column that's on the inside. We hold it above this. We move this back and forth, this white column here that we're going to call column 1, back and forth, up and down, until this 261 hertz tuning fork that I have right now becomes magnified, until it becomes much, much louder. When that happens, you've found one of the resonant frequencies of the air column. Okay? Standing waves are being produced, and it's been magnified. It's essentially a guitar. Again, we pluck the guitar string. What happens in the box behind the guitar? It resonates. Okay, we hear a louder sound, kind of an amplified sound by that resonating box in behind the guitar. We're going to hear something similar happening with his air column. Now, what are we going to measure? We're going to measure the temperature of the room, which I'll tell you right now is 20 degrees Celsius. We're going to measure simply by looking at the tuning fork what the frequency of the tuning fork is. There's a range of tuning forks that's going to be given to you in your kit. What I would suggest you do is use tuning forks of higher frequencies. Okay, the reason that I suggest you use higher frequencies is because you need less length of an air column if you have a higher frequency. You guys know this, right? Okay, you blow on the top of a pop bottle or a water bottle, If the water bottle is almost full, it produces a high pitch. If the water bottle is almost empty, it produces a low pitch. You need a longer air column with a lower frequency. So you're probably going to want to use a tuning fork with a higher frequency. That way you need a shorter distance inside that air column. You're not measuring the distance of the water, the length of the water. You're measuring, okay, the length here of the air column right here. The distance from the top of the white air column down to where the water level is. Because that's where the sound reflects off of, right? Is the boundary between the air and the water. It resonates in the air, reflects off of the water. The reason we use the water, because it's a nice, handy, convenient way to change the length of the air column really, really quickly and efficiently. So we move it up and down. As we move it up and down, this air column right here becomes longer or shorter. You want to change the value of that length until you hear this good, loud amplification or resonating tuning fork. Make some sense? So do a little demonstration for you so that you can know what you're expecting to hear here. Okay. Okay, the water's filled in there. Now I'm going to hit my tuning fork that has a frequency of 494 hertz. I'm going to hit it. I'm going to put it above. We hear 494 hertz. It's not quieter, but it's not louder when I hold it above either. Let's make it longer here. Again, I told you should expect to hear it somewhere in that 15, 20, 25 centimeter range. I need a volunteer here, actually. Can I get somebody just to hold this here? Thank you. Thank you, Riker. Just hold that. Thank you. I'll lift this up here. Okay, nothing yet. I'm at 11 centimeters. 14. You hear that? Do you hear that amplification there? Okay, so where's it at, Riker?
17
About 17 centimeters. You're going to have to play with it a little bit to get the loudest amplification you can. What I would suggest is that the person that's hitting the tuning fork and moving the inner column back and forth, that should not be the person that's trying to read the number off of it. Because what happens when I try to do that myself, okay, I think I've got it. I reach down to kind of look at it, and I move the inner column. I move column number 1, okay? So have the other person, have your partner or one of your two partners take a look at what that number is when you found the perfect distance here. So I hit it again. Rucker's going to tell me exactly what that number is when I hit the perfect distance. Right there. Right there, 16.5? Yep. So that's what we would write down then. Thank you, Rucker. That's what we would write down then for the length of the first resonance level in trial number 1. Okay, I would have wrote down 494 hertz here for the frequency, and I would write down 0.165 meters for the first length. Does that make sense? Now, you're going to have to go till you find another one. It's going to be a bigger number. It's going to be a bigger distance. Okay? Rucker, I do need your help actually again.
Estimate to be like 50 centimeters about.
So Rucker's guessing it's going to be about 50 centimeters. Okay, we'll go all the way up from 16 fairly quickly, though, until we get somewhere in that 45, 50, 55 range. We'll see if we hear it again. Okay, we're at 27 now, nothing yet. 30-ish.
40.
What am I at, Rucker?
About 45.
Do you hear that?
Yeah.
Louder? What are we at, Rucker?
51.7.
51.7. So Rucker predicted about 50. Turned out to be 51.7. Why did Rucker predict 50, by the way?
Because the harmonic is 3 times the first one, and the third one's about 15.
Yeah, it's a closed air column. It's a closed air column, so we know that the third one, the next harmonic that we're going to hear is the third harmonic, and it's going to be at roughly 3 times that one. So we measured, what was it again, Rucker? 51.5? 51.7, so 0.517 meters. You're going to do exactly the same thing with another tuning fork, although again, my suggestion is you use high values of frequency. If you start using low values of frequency, then the distance you get there might not be 50 centimeters, it might be more like 100 centimeters, and it's just more difficult to control this if you're dealing with distances of 100 centimeters. Okay, once you've got, thank you, Rucker, once you've got all of this data recorded, then you're going to go to your analysis. Your analysis consists of a number of questions, and they're on the back of the page. Okay, question number 1, calculate the speed of sound using 331 plus 0.6 times t. That's easy. We said the temperature is 20 degrees Celsius already. Okay, you've calculated that a bunch of times yesterday, okay, and already today on your quiz. Okay, easy enough. Then, this is the challenge part of this here. Okay, question number 2 says, using the equations derived in class for the first and third harmonics, okay, first and third, because there is no second harmonic produced here, calculate the speed of sound for each of your trials. Trial number 1 and trial number 2 both went with the same tuning fork. 3 and 4 went with the other tuning fork. So trial number 1 should have been a first harmonic. The frequency of the first harmonic, remember in a closed air column, was V over 4L. The frequency of the third harmonic in the closed air column was what? It's 3 times the value of the first, but that makes it 3V over 4L. We want to find speed. So let's rearrange this equation. V is equal to 4 times F times L. This one, to rearrange it, it would become 4 over 3 times F times L. Trial number 3, well, we'd go back to 4FL because, once again, we're dealing with a first harmonic. And then trial number 4, we'd go back to 4/3 F times L because, once again, we're dealing with a third harmonic. I want you to calculate the speed of sound in all 4 cases. Why are we doing that? Didn't we already calculate the speed of sound in question number 1? Yes, we did. Okay, this is our theoretical value for the speed of sound. This is what the speed of sound should work out to be. This is what the speed of sound does work out to be. The next question asks you to find the average speed. So let's take these 4 values that we just found, add them up, and divide by 4. Get the average value for the speed of sound. Then we're going to compare the theoretical value of the speed of sound. That's what we got in question number 1 with the actual value that we got, which is what we got in question 3. And then we're going to find the percent difference. Okay, in other words, we're going to find out how close our experimental value for the speed of sound turns out to be to the actual value for the speed of sound. Does that make sense? All right, a couple little things with this. Okay, first of all, we're going to go in groups of 3. Okay, groups of 3. We don't want any groups of 2 because we don't have enough apparatus to do that. Second of all, we do have 1 lab signed out, the biology lab signed out. We also have the classroom here, and we also have the atrium, okay, the atrium area as well. Okay, the reason that I want such a big area is not because we actually need physically that big of an area to do this. It becomes really difficult to hear your sound if you've got 10 other groups in the immediate vicinity of you producing the same sounds. Okay, so we want to spread out as much as possible. Go in the hallway there, okay, go in the hallway, the stairwell, okay, go in the atrium, go in the biology lab across the hallway, go in the hallway right outside the classroom, okay, stay in the classroom. Just spread out as much as you can. If you can't hear what you're looking for, again, remember, if you're dealing with the high frequency tuning forks, you're probably going to be, for the first one, somewhere in that 15, 20, 25 centimeter range. If you still can't hear it, then call me over and I'll give you a hand with it. Okay? All right, let's get at it.